So we are looking at what is called the linear operators, continuous linear operators. Gave you a proof from Lemay's book. I am not happy with the proof myself. I think it is unnecessarily complicated. So I will give a different proof. Okay, I mean almost the same type, but this proof is much easier than the other proof. Can you see the screen?
Yes, sir.
Okay. This is the proposition which I proved yesterday. Okay. This is from the dancer's book which I had sent it to you. Anyway, I should tell you some small stories here. See, every book has its own limitations and choice. The author who writes the book, whatever his fancy is, he does it like that. Okay. Okay. In this book, the notation is both E and F are vector spaces. Please note, they are vector spaces over the same scalars. Same scalars means the scalar on E and F should be same. Either both complex or both real. It's not that one is real, another is complex. That's not possible. Okay? All right. So when you write LEF, we mean the scalars on E and F are the same. Could be complex or could be real. Okay. If F is E, we write the notation as L of E. All right. Now, the main theorem which we proved last time is the following. For any linear operator from E to F, this operator T is uniformly continuous. The operator T is uh, in LEF. I don't know what you mean by LEF. Okay, let me see what LEF is. LEF means set of not LEF means the operator is continuous. Okay. So T belongs to LEF means T is a continuous linear operator from E to F. Third one, T is continuous at 0. Do you understand the statement of the theorem? You know the definition of uniform continuity? Hmm? You know or you don't know?
For function to be uniformly continuous, sir, uh, it should be sir, continuous for not just piecewise, sir. It should be continuous for the whole interval, sir.
The definition of uniform continuity, you are saying something different. Huh? Should I revise it?
Yes, sir.
Hmm?
Yes, sir.
Hey, you have to really properly understand. Huh? Okay. I will do it, okay. Okay, first, let me take T from E to A. There is some problem. T from E to A. This is linear. Okay. 1, T is continuous at X. If T of Tx y mod of this is less than epsilon, if distance of Txy is less than delta. So this, if for all epsilon greater than 0, there exists a delta depending on X and epsilon, such that this happens. Second, T is continuous on E if it is continuous at all points. Okay? Okay. 3, T is continuous, uniformly continuous, if for all epsilon greater than 0, there exists a delta, depends only on epsilon greater than 0, such that the distance of norm of Tx minus Ty is less than or equal to epsilon if the norm of X minus Y is less than delta. Okay, so this delta is independent of X, then it's called uniformly continuous. Normally you talk about uniformly continuous on a subset, but here we are saying uniformly continuous on E. Okay, so this is normally stated as saying that it is uniformly continuous. Whenever you say that T is uniformly continuous, what we mean is T is uniformly continuous on E. Okay. Now, second thing is T. Obviously, if T is uniformly continuous, it is definitely continuous. If it is continuous on the whole space, it is continuous at 0. Third thing is T is bounded. T is bounded means it maps bounded sets to bounded sets. Okay. That's what it means. Bounded set means. Okay. So definition: bounded sets. U of a subset U of E is called bounded if there exists an M such that this U is contained in a ball of radius M. Or otherwise, you can say that every element of the U is less than or equal to M. All right. This is the last one, fifth one. There exists alpha greater than 0, such that norm Tx is less than or equal to alpha times norm X for all X in E. So what it says is all these statements are equivalent. If one of them is true, all others are true. So how do you prove this result? You first prove 1 implies 2, 2 implies 3. And then later we'll go back to 3 implies 4 implies 5, etc. etc. 1 implies 2 and 3 implies 2 implies 3 are obvious. If it is uniformly continuous, necessarily it's continuous. If it is continuous on the whole space, it's continuous at 0 also. So it's obvious. Okay. Now we want to show that now that T is a continuous at X equals 0, so we assume that T is continuous at 0 and show that T is bounded. What do you mean by T is bounded? You have to show this. Okay. You have to show this part. That norm of Tx is bounded by M for all whatever that M is. Okay. So you look at this T to be continuous at 0. What do you mean by T is continuous at 0? There exists a delta greater than 0 such that norm of Tx is less than or equal to 1 whenever norm of X is less than delta. Here you are taking epsilon equal to 1. Okay. Usually they say that given an epsilon greater than 0, there exists a delta, etc. Forget about all those things. Take epsilon equal to 1. There is a delta. Okay. So whenever norm x is less than or equal to delta, then norm of Tx is bounded by 1. Now you define M to be supremum of x belonging to U. U is the unit ball of radius R. Okay. So that delta by M into norm x, delta by M comes out. You get norm x here. Okay. That is less than or equal to delta. That is because norm x is uh, so this norm x is less than or equal to M because this x is in U. If x is in U, norm x is less than or equal to M. So this M cancels, you get delta by M into x, norm is less than delta. Since this is satisfied by the definition of the continuity, the T of delta M by x norm is less than or equal to 1. That's what the continuity of continue at 0 is. Now take that delta by M common because out of T because T is linear. You get delta by M into norm Tx equal to T of delta by M into x f because of linearity. That is less than or equal to 1. What does it mean? It simply means this norm of Tx. So you remove this delta M out and push it on the right side. You can push it on the right side because both delta and M are positive. So inequality still it stands. So norm of Tx is less than or equal to M by delta. This is the bound that we are looking at. So therefore, under the image of T under T is bounded. What is the bound? Bound is M by delta. So this shows that 3 implies 4. So this shows that 3 implies 4. And then 4 implies 5 is simple. Okay, I will leave it to you. So this proof is much simpler than the proof which I gave yesterday. But anyway, you choose whatever proof you want. So now what we do? Any comments? Any questions?
Sir, how we can say norm of Txf less than equal to 1 at the in the proof, sir? You have earlier told that take epsilon equal to 1. That's why is less than equal to 1. Yeah, any other concept is there?
What is this delta? You choose delta. How do you choose delta? Take epsilon equal to 1. So
Okay, sir.
then
If we take epsilon,
take epsilon equal to 1. Okay.
okay,
There
sir.
is a delta. Capture that delta.
Okay, sir.
Yeah. Now take
Okay.
any x in U. When you take x in U, multiply and divide by delta by m. But U is set of all. This is the U is the a subset U. It is in the ball of radius m. Okay. This U is contained in the ball of radius m. Therefore, every element of the ball of radius m will be less than norm will be less than or equal to m. Right? Is it okay, Rishabh?
Yes, sir. Yes, sir.
Okay.
Yes,
Now
sir.
what you do is when you take this x in U, its norm is less than or equal to m. So delta by m into x is delta by m into norm xe, but this is less than m. So this m cancels. What you get is a delta. So this element, if you call y equal to delta by m into x, y is the norm is less than or equal to 1. If that norm is less than or equal to 1, t of that is less than or equal to 1 because of continuity at 0. Click.
Okay, sir. Okay,
Should I
sir.
write it?
No, sir. No, sir. Clear.
Oh. The proof is very simple actually. So that's the story now. The other part is also simple. You do that yourself. Okay. So the proof is simple here. How you prove is 1 implies 2 implies 3 implies 4 implies 5. and 5 implies 1. 5 implies 1 is obvious, okay? Because this alpha is independent of x, okay? That's why. All right. Do you understand 5 implies 1 is simple? Should I do it? This is the 5, okay? I'll let you read it. Now we define what is called the operator norm. So on this set of all linear operators from E to F, continuous linear operators, we define the norm. What is this norm? Norm of T is bounded by infimum of alpha greater than 0, such that norm of Tx less than or equal to alpha times norm x. So how do you, this is true. Norm of Tx in F is less than or equal to alpha times norm xe is true because T is a continuous linear operator. So such an alpha exists. Since such an alpha exists, you take the infimum of that. Okay? They are not saying whether it is positive or negative or something. Okay? Don't worry about that. This is called an operator norm. I'm only saying it's called an operator norm. Okay? We are going to prove that it's a norm now. All right? Okay. You can also do, so you say that that this, whatever the theorem we have shown, it actually shows that this particular L of EF is bounded if and only if norm of T is bounded. That's okay. Do you understand it's a norm?
By definition, it's clear, but sir,
Yeah, but why, if T is not 0, why alpha is greater than 0? That's the question.
yes, sir.
Hmm?
Yes, sir.
Should I do it or leave it to you?
There
No,
is
sir.
a
Just
property of norm
explain,
also,
sir.
sir,
You
by
do it
that.
yourself. If you have problems, I'll come back to it again. So that this definition that what we have given here is a bit useless definition, not very helpful one. So we find out equivalent definition for this particular thing. So suppose T is a continuous linear operator from E to F. Continuous linear operators, they are also called as bounded linear operators. Let me explain to you this matter, okay? Because when you read some other book, you should not get into problems there.
Sir, I have one more doubt, sir. How
Hmm.
to follow the norm property, sir? Like if we define any norm.
That is what I asked you. You said it's obvious. That's why I kept quiet.
No, it's like by definition, sir, it's looking, but just I want to like if I define norm in metric space, there are some property 3 to 4 that satisfy, then it's
That
then
is
how?
what I asked you. Is it clear to you it's an RM? You said yes. So I kept quiet. Shall we verify it?
Yes, sir, yes, sir.
Okay. 1 minute. Huh? You see, this norm of T is defined to be infimum of alpha such that norm Tx is bounded by alpha times norm x for all x in alpha. This is the definition. Okay, let's take first one. Let's take norm T equal to 0. Okay, this I take it as 0. This infimum is 0. Okay, so what I am saying is this infimum is 0. Does it follow that T Tx is 0? Does it imply
Yes, sir. Yes, sir. If then that means if
this is true, right?
yes,
No,
sir.
sir.
Pardon?
Because sir, if norm of t equal to 0, that means our alpha equal to 0. If our alpha equal to 0, then our norm
Why?
of tx.
Huh? Your infimum of alpha is 0, right?
Yes, sir.
So why infimum is 0?
So because alpha is defined for greater than 0, so least value possible is 0.
Yeah, but how do you know infimum is 0? Okay. Let me take Tx equal to 0 for all x. Okay. Then this implies and by implies norm Tx is 0 for all x. That implies that alpha is 0. Okay. Because for all alpha, this is 0. Both sides are 0. So alpha infimum is 0. Okay. You are taking the least positive number. So alpha greater than 0. Is it clear? My question is something else. If this norm t is 0, does it imply Tx is 0 for all x? That's what I am asking you. What is that you have to show? Three conditions, no? Norm t is 0, if and only if t is 0, right? If t is 0, then it's obvious. No problem. Suppose norm t is 0, why should Tx be 0? Suppose there exists x in E such that norm x is not 0 and Tx is not 0. Suppose. Then norm Tx, it is bounded by norm T, okay, is less than or equal to this alpha times this norm x, right? Since you are taking this norm to be 0, so if this alpha is not 0, then norm T is not 0. Because this has to be less than or equal to alpha, for all x, okay, for all x in E. So if this is not true, there is an alpha for which this norm is this alpha is not 0. That's the infimum is not 0. Then that shows that this t norm t will not be 0. So this is true. So the second property is norm of alpha t is mod alpha times not alpha. Okay, norm of some a times t is less than or equal to mod a times c. That's obvious because that infimum comes out because this a is independent of this. Right? Now, if you take tx plus y, okay, norm of this, that is less than or equal to norm tx plus norm ty, etc., 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 etc. And then you can show using this, the infimum is also less than. So that's what I'm saying. You have to verify the three conditions of the norm. Okay. You have to verify the three conditions of the norm when you define this norm to be Where is that now? Yeah. When you show that this whatever the right side is 0, if and only if this Naram T is 0. That you can show it. That is simple. So that's what I proved to the third one. You prove it. If you don't get it, we will do it again. All right. We could define Naram T in a different way also. Okay. Now, anyway, we could define T for all T in homeopaths. But theorem 8.3 says that T is a bounded linear operator if and only if the Naram is bounded. Okay. Before proving the operator for operator Naram is in fact a Naram, we first give characterization for this. Okay. This is what he says. Before proving the operator Naram is in fact a Naram. Okay. We will do that. Now, suppose T is in LEF, then Naram of Tx is bounded by Naram of T alpha x into E. This is true for all x in E. Moreover, Naram of Tx is equal to Naram Tx by Naram x not 0. Take this supremum. Otherwise, you take the supremum on the sphere, etc. 8.1. So all these are equivalent, whether you say bounded linear operator or whatever it is. So let us fix I don't know whether you are getting what this man is trying to say. We have not yet proved it's a Naram, but what we are saying that whatever that Naram T you have defined there, if you don't want to call Naram T, call it as beta. Okay, call that beta. This infimum stuff, whatever this infimum stuff we have here, this infimum you have here, no 8.4 definition, call the right side as beta. So what we are saying is this beta, whatever that beta is equivalent to supremum of x naught in 0, Naram Tx over Naram x. Why are you taking the x naught 0? Because you are dividing by Naram x. Second one is supremum of the unit sphere of Naram x is same thing as the supremum of Naram Tx over Naram x. And these are equivalent 8.1. Okay. So that beta is the same thing. Let me explain to you. Okay. I have to write somewhere else. Okay, just wait. Where do I write? Let me save this. Okay, I'll come back to it. 1 minute, just wait. File save. Just wait. Okay. So we have 5 quantities here. Okay. Let me call, say, K1 equal to infimum of alpha greater than 0 such that Naram Tx is less than or equal to alpha times Naram x. This is important for all x. This is one quantity. Second quantity is K2. This is supremum of x naught 0, supremum over x naught 0 of norm Tx over norm x. This is K2. K3 is supremum over norm x equal to of norm Tx. Divided so for norm x less than or equal to 1. Okay, these are four quantities we are defining. I am not saying whether this is a norm or not. The claim is K1 equal to K2 equal to K3 equal to K4. Okay, wait for the proof. Proof is given there. Suppose this is true. Okay, suppose assume this is true. Okay, if the supremum is 0, then therefore norm of Tx by norm x is 0. Right? Supremum itself is 0. Therefore, it cannot be. So for no x, so this will give you K2 equal to 0 implies Tx is 0 for all x. Yes, correct. That gives you T is 0 operator. If T is a 0 operator, then norm Tx is 0 divided by something which is non-zero. So this is 0. Supremum of 0 is 0, nothing more. So this also implies that norm T is equal to 0 implies that K2 is 0. So the Tx equal to 0. So norm T equal to 0 implies and by implies T is 0. This is the first thing which I was explaining to you earlier. Now what this theorem says, what we are proving is this: K1 equal to K2 equal to K3 equal to K4. This has to be proved, right? That is the theorem. First you prove this, then you can show that it's a norm. So the notation here is the following. Sorry. So the notation here is slightly, here it is an operator norm. It is still not a norm. So call this as K1 on the right side. Okay. And then you call this second element as K2, third element as K3, K4. Now what we are showing is that all these things are same. Okay. That is the theorem. This is the proof of the theorem. Suppose T is in LEF, that is T is a continuous linear operator. Set A equal to alpha greater than 0, such that I called it as K1. Now he calls it as A. Okay. Now he calls it as A here. So norm of Tx is bounded by this. By the definition of whatever this A, okay, is not whatever that the infimum of all such elements is actually we are denoted by the two lines with D. I called it as a K1. All right. So if alpha is in A, so take an alpha for which it is in this set A, that is there exists an alpha for which this is true, then norm of Tx is bounded by alpha xt by the definition. Therefore, norm of Tx is less than or equal to alpha times E by the definition of the set A itself. And therefore, x belongs to E. Right? Hence, for x belongs to E, norm Tx is less than or equal to infimum of whatever that K1 is less than or equal to infimum of this. Proving the claim, right? That we have proved the claim that norm of Tx is bounded by norm of whatever that K1 into norm X. That's the first thing. All right. So this part of the proof is the first line of the proposition. Now we come to the moreover point on this point. Okay. Now we set lambda. So we set lambda equal to now supremum of norm Tx or norm X not 0. We are taking X not 0 because we are dividing by norm X. I called it as K2 in that whatever the thing is. Now, when you are taking this supremum, right, is lambda, obviously norm of Tx over norm of this X is bounded by lambda. You take any X, right, this right side X, then norm of Tx by norm of E will be less than or equal to lambda because lambda is supremum. Therefore, norm of Tx is less than or equal to lambda times Xe for all Xe. So, there is a lambda for which norm of Tx is bounded by norm of this X. So, since this set, whatever the first one K1 is the infimum of all such lambdas, obviously this lambda will be greater than or equal to infimum of A. That is what we have called it as this. So, lambda will be greater than A. So, what we are saying is that K2 is greater than K1 in our notation. And you continue the proof, and so the proof is not a very difficult proof. Okay. So, what we have shown is that lambda, whatever this lambda, is greater than, that's also less than or equal to lambda t. That is a consequence of what we have shown in the first part, that norm of Tx is less than or equal to whatever that K1 into norm Xe. Okay. All right. So that gives, now going from X not equal to 0, etc., combining these two inequality, we get K1 equal to K2. Going from X not equal to 0 to something with norm X equal to 1 is an obvious thing. You take any X and then you do the standard calculation here. Let me see whether I can show it to you. Okay. What I'm trying to tell you is that you take K2 equal to supremum of X not 0 norm Tx by norm X. And you take K3 equal to supremum over norm X less than or equal to 1 of norm Tx. What I am saying is that these two are equal. Okay. How do you show this? To show this, you show that K2 is less than or equal to K3 and show that K3 is less than or equal to K2. And this will imply K3 equal to K2. Okay. This is the proof. Now, this supremum, this supremum of norm Tx over norm X, this is for all X, okay? X not 0. This will be greater than or equal to supremum norm X less than or equal to 1 of this supremum. Right? So this is less than or equal to 1. All right. If you want, you can put an RM here. Now this is true because this supremum is over a large set. X not equal to 0 means X is in E. So this supremum is over a large set. So you can put an RMX here. So therefore this supremum is larger than this. Therefore this K K2 is greater than, rather K3 is less than K2 is obvious. Now, how do you prove the other part? The problem is that we have to go from norm x. So take x not 0 and you look at y equal to x divided by norm x. Then this is this norm of y is 1. Right? In fact, less than or equal to 1 if you want. Now apply K3, right? So T of norm T of y divided by norm y. This will be greater than or, this will be less than or equal to this K3. Push this on this side and now you take the supremum. So you get the other part. This is a standard proof which is used in function analysis. If you do something on the unit sphere, it will spread over the whole space, and if you do for the whole space, you can reduce it to the unit sphere here. That is what this proof is. Okay. So he calls this as beta. Okay. So you take the beta supremum of t less than equal to norm tx. Now what you do is this will be less than or equal to supremum of norm x divided norm tx over norm xe, right? This is obvious, huh? Why it is obvious? Since norm x is less than or equal to 1, norm of tx is less than or equal to norm tx over norm, right? This denominator is less than 1. So norm of tx will be less than or equal to this part. This will be larger. You take a supremum here, you take a supremum here. You take a supremum here, you get this. That's it. So that gives you that this beta is actually equal to lambda, less than or equal to lambda. And you similarly show for every x6, you divide by this and then you let epsilon go to 0. You get the beta also the greater than or equal to lambda. So this beta is this quantity, supremum over the whole space, and sorry, lambda is that, beta is supremum over the unit ball norm x equal to 1. So beta greater than or equal to lambda, lambda greater than or equal to beta. So that is how you prove it, and you get all the qualities. Now, after getting this one, now we can show that this T is a norm. Okay. So let G be, this is by the definition, the supremum. So we want to show it's a non-linear space. For that, we have to show that it's a norm. This norm T is greater than or equal to 0 is obvious. Now let the norm of this T be 0. Then the supremum of norm Tx over norm xe is 0. How do you get this one? You get it from this statement that all these things are equivalent. Okay. So from that statement, the supremum is 0. If the supremum is 0, obviously every element has to be 0 because every element is positive. So norm Tx over norm xe is 0, but norm xe is not 0. Push it on the other side. You get norm Tx equal to 0 for all x. Norm Tx equal to 0 all x if and only if Tx is 0. So that shows that Tx is 0 for all x. Therefore, T is a 0 operator. Right? So now next is the norm of lambda T. You show it to be mod lambda into this. This is an obvious affair. Not a very difficult thing. Now you want to show the triangular inequality. So take two elements S and T, two elements, two operators S and T, which are linear and continuous. Now you look at the norm of S plus T. Since S is linear, both S plus T will be linear. So you can define the norm of S plus T, that is supremum over the norm x equal to 1 of norm S plus Tf, that is less than or equal to this one. Why? Because norm of S plus Tx is less than or equal to norm Sx f plus norm of Tf by the triangular inequality. since the inner quantity is smaller than this, supremum also will be smaller than this. And therefore, you take the supremum splits over the two things. You get norm of S bounded in LEF and supremum L of EF in this one. That shows that norm of S plus T is bounded by norm of S plus norm of T. That proves the triangular inequality of the norm. Therefore, it becomes a norm. So the obvious thing is that this LEF now becomes a non-linear space. Set of all bounded linear operators from E to F. So this one is a non-linear space. Now next we show that it is a Banach space. So if the range space, if F is a Banach space, then LEF is also a Banach space with respect to the operator norm. This proof will take a bit of time. Bit of time means about 10 minutes time. Since we have, it's already 12:52. So let me give this theorem the next time. This part of the proof, for the this part of the proof, what we are giving now, is actually tells you the set of all bounded linear operators from E to F is a Banach space. All right. Something is happening. I don't know what is happening. Okay. So the time is 12:52. So on Thursday we will do the other part. So you read it up from this part of the book. This proof is very simple, much better than the proof which I gave you from Lemier's book. Anyway, you read whatever book you want, but be clear about it. Okay? Maybe, if possible, I will try to do functionals on the next class. Bye. Have a good day.
Bye, sir. Thank you, sir.
Welcome. I'm
Thank
leaving.
you, sir.
Welcome. I'm leaving.
Thank you, sir.
Most welcome. Bye, Rishabh. Bye, Sonu.